This lesson starts out with stuff we've already talked about, so I'm going to go really fast, okay? Vocab review. When you draw an angle, we always put its, if it's talking about something on the coordinate plane, we put its initial side at the positive x-axis, and then however far it rotates around and we stop, that's called the terminal side. So it'll say the terminal side is in quadrant 3 or something, and that means it looks like this. Then it went this way. We good? If it's positive, if we happen to decide it went this way, then it's negative. We good on all that stuff? Okay. Just reviewing all that real quick. Ooh, new stuff. You may have done this if you had trig, but it's on the quiz. It should be super easy points because it's all done on the calculator. It can be. This is particularly easy to do on the calculator. You just type. Everybody got their calculator out? Let me get mine out. Okay, there we go. For this one, I'm going to type 56.735. And I want it in what's called degrees, minutes, and seconds. You know how we can take a mile and break it down to feet, or we could do yards and then feet and then inches? Okay, well, an angle can be broken down, but it's more like time. You know, we have a day is so many hours, which is so many minutes, which is so many seconds. Well, a degree is also broken down into minutes and seconds. And it's also based on 60 because they're evil. Okay? So there's 60 seconds in a minute and 60 minutes in a degree. But our calculator has a magic little ability to do this. There is an angle button. Okay? It's second and then the angle, which is the apps button. Everybody find it? Because you're going to want to know this for the quiz, and it's not something we're going to practice very much. So second, and then the apps button. And we want to change this into degrees, minutes, and seconds. Anybody see what we're going to do here? Yep, choice 4, which is change this into degrees, minutes, and seconds, and hit enter. And we get that this should be 56 degrees, 44 seconds, and 6 minutes. Let me show you the long way, just so you know where this came from, okay? Back in the day, I would have taken that number and subtracted off the 56 and written that down on my paper because that's the whole degrees. That makes sense? And then this part, this 0.735, I would have said, well, that's a part of an hour, or in this case, a part of a degree. So I'm going to multiply by 60 and get 44 minutes. And then that decimal, that 0.1, is another part, but it's a part now of it's a part of a minute, which is seconds. So I would take that times 60 again and get 6. So that's how I would have done 56, 44, and 6 the old way. But you're all going to be happily using your calculator, yes? Okay. The other direction is much trickier on your calculator, and to be honest, I always do it by hand. But I don't expect you to. Okay, this is 32 degrees, 5 minutes, and 28 seconds. How many seconds in an hour? This is really important. In an hour on the clock, how many seconds? It's not 60, right? It's 60 times 60 because there's 60 seconds in every minute and 60 minutes in an... Let me try that again. Yes. So if this is degrees, minutes, and seconds, it's like hours. So there's 3,600 seconds in a degree, like there's 3,600 minutes in an hour. When I asked that question, I don't know if I said minutes or hours. I meant hours, but all right. So when I used to do this question right here in the good old days, and I still do it this way, honestly, I would say it's 32 plus 5 divided by 60 plus 28 divided by 3,600. Okay, 32 plus 5/60 plus 28/3600, because that's how many seconds in a degree or seconds in an hour. And I'd get this lovely number, which they rounded to 0.091. Okay. If you want to do it on the calculator, it's a little bit of a nuisance. All right, so we're going to put 32, and then we're going to go back to that angle menu, which is what? Second apps. And we're going to put in the degree symbol. Got it? That wasn't so bad. And then we're going to put a 5 on our screen right after that degree symbol and go back, second apps, and go down to number 2 and put the minute symbol. And then we're going to type 28 right behind that. And then this is the pain. It's not in there because you use the quote marks when you do programming. So they have it on the actual home screen of the calculator. It's alpha plus. Do you see it there? So alpha plus will give us the seconds, and then we'd get that 32.09111. Okay? So I just find it a pain in the neck, so I usually do plus how many 60ths plus how many 3600ths. But I don't care which way you do it. You just got to know how to do one question for the quiz. Does that seem all right? All right, so can we practice these two on our notes? Can you do this one? Tell me what you get. This is the easy kind. You just put it in as a decimal. And then go, I want this DMS thing, choice 4. I got 2, 13, 52, and 30. Did someone else get that? Everybody else get that? Anybody stuck on how to get that one? All right, the other direction, more of a pain. On the calculator, it would be 89. Now, if you want to do it my way, it's 89 plus 56/60ths plus 7/3600ths, okay? If you want to do it their way with the calculator, it's degrees, minutes, wrong button. Just kidding. Still working. Hang on. Alpha, this one, right? Did you get that? 89.9352. I don't know what they did. Maybe rounded it? I forgot something, didn't I? There's a 9 there. Anyway, something like that. Disgusting answer. Any questions on that? All right. Measuring angles in degrees is appropriate when applying trig. Okay. For other applications, we use a lot of radians. Okay. For other applications with trig functions, such as using angles measured in degrees, poses a significant problem. A degree has no relationship to any other linear measure. There's no such thing as an inch degree or inch per degree. It has no meaning. All right, so then measuring angles in radians is the solution to that problem, because radians will divide out. I always say it's like a magical unit. It just appears and disappears, okay? So here's a formula you need to know, but it is on the pink sheet. You just need to know how to use it, okay? The measure in radians of a central angle is equal to the ratio of the length of the intercepted arc to the radius. So theta equals S over R, or the angle is equal to the arc length divided by the radius. We're also going to move that all around, and we're going to say things like the arc length is equal to, how do we get S by itself there, guys? Yeah. Remember using that one ever in trig? Okay. Right. Notice that as long as the arc length S and the radius are the same linear units, then this turns out to be the S over R turns out to be unitless, and that's then said to be radians. All right, we have already covered converting. Does anybody need me to go back and forth between angles and degrees and radians? Okay. And this is on your notes, but we just discussed this, yes? Going this way is positive and this way is negative, but these are called coterminal. Why are they called coterminal? They end in the same place, right? You stop measuring in the same place. All right, we're going to revisit coterminal, that word, one more time, because these two questions below ask for all answers. So we're going to leave things in terms of a variable. Remember, I said I always put plus or minus right here just to remind myself I can go either way. As long as n is any integer, it could be a negative number, so you don't have to put that plus or minus. You can just put plus. And if it's in radians, we do plus or minus 2 pi n. All right, so if it said all angles coterminal with this in its degrees, we'd put 45 plus or minus 360 n. If it's in radians, we'd do negative pi over 3 plus or minus 2 pi n. And we're supposed to say where n equals any integer, but I'm not going to make us write that. So this is on our notes real quick. If they wanted all the angles ever that lined up with this one, we would say what? You would keep adding or subtracting multiples of 2 pi because it's in radians, okay? And because this is our notes, I'm going to write where n equals any integer, but you don't have to have that. All right, what about number 3 here? If they started at 135, then when we do plus or minus, we have to do 360n. And number 4, you just have 5/3 pi plus or minus 2 pi n. All right, are we good on that? That was review as well. And why did we have to do leave the n there? Yeah, because it says all angles, okay? If they just wanted one, we would just do it once, right? And give them a new answer. All right, go ahead. You don't. You don't have to write that. I'll accept it without. Okay. All right, guys, this is arc length, which is what I talked about a second ago. It's just rewriting that formula. Instead of solving for theta or writing theta, we're going to write S equals. But you have to have the angle in radians to use this formula. If they give it in degrees, we're going to have to convert it to radians. Okay? So on your notes, it looks like this. And it does say here in radians, so make sure you see that or note that when you see what's on the notes. Okay, this formula only works in radians. It also says that on the pink sheet. Does everybody see where it is on the pink sheet? I think it's on the side with the unit circle. Yes, right above it. Is that right? Anybody have their pink sheet out? Or everybody should have your pink sheet out so you're familiar with where these formulas are. It's at the above the unit circle, I think. And I think it specifically says these formulas work in radians, yes? Okay. Giving you all the hints I can give you. All right. So it says, suppose an object moves at a constant speed along a circular path r. If s is the arc length traveled by the object during time t, then the object's linear speed, okay, linear speed is the length of the arc divided by time. I don't ever use these formulas, honestly. I just do dimensional analysis, okay? Anything that wants a linear speed is distance per time. If theta is the angle of rotation in radians, the object moves, then the angular speed, which is this funny little W thing, which is actually an omega, is given by omega equals theta over t. Okay? It's like a lowercase omega. All right. So in the notes, again, here's the formula, but I don't ever use these. I just remind myself that if it's a linear speed, you guys know linear speed. It's miles per hour, right? Feet per second, something like that. So the labels, it's got to be distance per time. For example, you could have miles per hour, kilometers per hour, you could have centimeters per second, etc., okay? If we want angular speed, which is this goofy little mega, then you need some kind of angle per time, and it's always going to be radians per time for our purposes. Okay? So you could have radians per second, radians per minute, etc. Everybody get the idea? The difference between angular and linear. Okay. Let me give you another example. When you're talking about a bicycle wheel, okay? You're riding your bike. The linear velocity is how fast you're tracing out a line or you're going down the road, okay? If you chalked up your tire and you rode down the road, you would leave a line behind you at so many centimeters per minute. Does that make sense? Angular velocity is a different concept. Angular velocity is how fast this is turning, okay? How many degrees in a minute was what my brain thinks, but it really is measured in radians, okay? So it's how many radians per minute or second is this turning at. All right. So real quick, you have this example worked out, but just help me work through it up here. It says, determine the angular speed and the linear speed if 8.2 revolutions are completed in 3 seconds. Okay, 8.2 revolutions in 3 seconds. I told you I don't use formulas, I use dimensional analysis. Is revolutions per second an angular or linear velocity or neither? Neither. Okay, it's almost angular, but they tricked us. What does angular always have to be in? Radians. So we need to change revolutions to radians. What do we know? 1 revolution is 2 pi radians. Again, I'm just using dimensional analysis to get rid of revolutions. And I'm going to type 8.2 times 2 pi divided by 3 when I type it in so that I get radians per second. Calculator. 8.2 times 2 pi divided by 3. I got 17.2. Anybody else getting that? Says around to the nearest 10? Yes? No? Okay. Is that what they have down on the paper? Okay. And then it wants also the linear speed. Now, to have a linear speed, I don't want radians anymore. Okay. I need a distance. So the formula that sticks in my mind is to get from angular to linear, you multiply by the radius. But what I really know is I need to change this answer, 8.2 times 2 pi over 3, which is right now in radians per second. I need to get it into a distance. Well, what do we know from the problem about a distance? Yeah, it says the radius or the distance from the center is 7 centimeters. Now, this is where that magic comes in. Do you remember I said that radians can just appear and disappear? Okay. If you multiply this answer by 7 centimeters, this goes away and you just get centimeters per second. Okay. So if we do that, take that number that was on our calculator and multiply by 7, I have 120.2 centimeters per second. Is that what they have for you? I don't know if they left it exact or not. This is about the only formula I keep in my head besides this one. Okay. Oh, no. R times theta, right? Let me confuse you completely. Again, this is linear velocity equals angular velocity times the radius. All right, everybody got what they want off that slide? All right, so this is a dumb question. This is already an angular velocity. It says 2.7 radians per second. For some stupid reason, they want us to change it to revolutions per minute. Okay. Well, if you work in a factory as an engineer, you need to know RPMs, which is revolutions per minute. Okay. So we're going to change this from radians back into revolutions. So what do we need to do there? Yes, how do we get rid of radians and go back into revolutions? So 2 pi radians is equal to 1 revolution. Now, I'm going to warn you right now, this is a hot mess. Because if you type 2.7 divided by 2 times pi, is your calculator going to divide the pi in the denominator? No. So you're going to need parentheses there, okay? It also wants this in minutes, guys. So what do we need to do to get this back to minutes? 60 seconds right now is on the bottom, seconds, right? We want to cancel seconds. So we're going to say 60 seconds is 1 minute. Okay, seconds and radians will cancel, and will we have what we want, revolutions per minute? Okay, I'm really worried that if this was on the quiz, a lot of you would type it wrong. So please practice. If you go all the way across the top, you're really just doing 2.7 times 60. And in the denominator, you really just have a 2 pi, but you have to put those parentheses in. You don't need the first parentheses. You can just type times 60. But when you divide by 2 pi, you need the parentheses. Honestly, don't think I put that on the quiz, but I got 25.78 if we did hundredths, or 0.8. Anybody getting that? Okay, that is RPMs, or revolutions per minute. What's different about number 6? Anybody struggling here? Are we okay? Okay, same as the last one, we need to go back to revolutions, but it wants minutes and it gave us what? Hours this time. So we have 2 pi radians, still going to need parentheses around that, is 1 revolution. But I need minutes. So what am I going to do? 1 hour is 60 minutes in the denominator. I don't know if I can move all that, guys. Nope. I wrote really small over there. Can you see it? All right, so I have 4 pi over 3. The hours drops out. Then I have a 2 pi down here. The radians dropped out. And I have a 60 to get to minutes, right? The hours canceled out. So what am I typing? Well, the only thing in the numerator is what? 4 pi. What's down in the denominator? 3 times 2 times pi times 60. And that is all in the denominator. All right. It's actually 1 over what? 90? You can do it all on your calculator, but you just need a big parenthesis around the denominator. 3 times 2 pi times 60. Anybody else getting 0.01 repeating? Which should be 1/90th if I did it in my head right. Okay. What's the label again? RPMs. Okay. I don't know what's turning that slow, but it's turning really slow. Okay. 0.01 revolutions per minute. Okay. That seems really, really slow to me, but it depends on what it is. Okay. If it was a gigantic gear or something, might not be as slow as it seems. Okay. We're moving on to find the radius. What? Find the radius. Okay. Any ideas? I'm thinking we need the formula I just talked about. Angular equal, or linear equals angular times radius. That's how I would think about this. If we have 24.8 meters per second, and there was some revolutions per minute. Oh my gosh, they're making this so miserable. We need to figure out what radius was. So we're going to work backwards, but what do we got to do with this hot mess first? Change it to radians. 1 revolution is 2 pi radians. What else do we need though? We got minutes and seconds here. I'm thinking we need to go to seconds because we want to divide this out eventually. Let's see, minutes is in the denominator, so 1 minute is 60 seconds. So that will divide out. Okay, so I have 24.8 meters per second on this side. Over here, when I multiply that all out, what do I get? 120 times 2 pi divided by 60 should be 4 pi, or I get 12.57 if we round. Okay, and what's the label on that side? Radians per second. Now we're trying to find this radius. So we're going to need to do what? Divide. And I know that's going to get some of you kind of confused. It's not, because we're getting rid of multiplication. But as far as the label thing goes, when you divide, what happens? You multiply by the reciprocal. So we're really doing this. And that becomes seconds over radians. So the seconds cancel and we get just what? Meters, because remember the magical unit of radians disappears. Okay, 24.8 divided by that answer. Anybody getting like 2, basically? 1.97? I don't know. Did you get 1.97 or did you get 2? I did it exactly. Okay. And that would be, what was the label left? Meters? Okay, that was really icky. I'm going to skip 8 because honestly, I'm not going to ask you this question on test or quiz. There's one on the homework. You can follow that one in the notes. Number 9. I like this question, so I'm going to do it real quick because it says a curve on a highway has a 1,000-foot radius with lanes that are 14 foot wide. I'm going to do 14 feet for each lane, okay? That's why this says 28 feet further across. It says if the curve makes a 180-degree turn, how much longer is the outside edge of the far lane than the inside edge of the close lane? So there's a difference in radius of 28 feet. What do we want to know if we want to know how much further it is? How much more what? Arc length. Perfect. Okay. So I want to know the arc length. What's the formula for arc length? Okay. So we need R, which is 1,000 here, and 1,028 here, times theta. Ugh, that was not good. What's theta, guys? Well, theta is the angle. What did they say in the question? 180 degrees, but can we use 180 degrees? We need it to be in radians. What is that equal to? 1 pi, right? So we're going to multiply this by pi and this by pi. So 1,000 pi is something like this. 1028 pi, I didn't type it right, is something like this. Someone get that? So what's the difference? It says how much longer. So the difference is I got about 88 feet longer. Okay. Yes. It says is the outside edge of the far lane. Yep, yep. I agree. I'm just doing what the question said. It said inside edge to outside edge. Yes. That's not necessarily the difference your car would travel. You'd probably have to average like the middle of each lane or something. But the idea is simply showing you that there's a reason they take the inside lane when they do the NASCAR turn, right? They're saving some distance. Yeah, yeah. I just did what the question asked. All right. Area of a sector, guys. We do have one more formula to talk about today. And then we have some practice and applications. This is on 6A, yes? Okay. A sector is a wedge. It is a sector of a circle is a region bounded by a central angle and its intercepted arc. It's all the area inside there. So the formula is on your sheet. You don't have to memorize it, but it's 1/2 r squared theta, where theta has to be in again, radians. All right, so we're going to do a little practice. It says, what area does she use for tomatoes on this question? These are really hard to read, but these are degrees. Okay, and tomatoes, it says, is 50 degrees. So we want the area for 50 degrees when the radius is what? Anybody see that in the problem? The radius is 10 feet. Okay, so the formula for area is 1/2 r squared times theta. But what do we have to do to theta? Change it into radians, which means we're going to take that 50 and multiply it by pi over 180. Do you need me to go through the dimensional analysis of that, or you remember that how to change degrees to radians? Okay, so 0.5 times 10 squared times 50 pi divided by 180. I got 43.6. Anybody else? And what would that label be? Yep. Oh, I'm so sorry. 43.6 square feet, because this didn't have a label. This was feet and we squared it. And remember, radians goes away. Okay, we divided out the degrees when we did that. All right, I'm going to skip B. I think we could do the same thing with wildflowers. Actually, I think we'd have to like figure this all out and subtract from 360, but we're just going to, oh, we have to do it for this one anyway. All right, we'll do it. Oh, no, we don't. If this is 80 and these are the same, this is also 80 degrees. So how many total degrees of area is she using for wildflowers? 160. Okay, then we need to multiply by pi over 180 to get radians. And then we need to find the area, so we have to do 1/2 r squared times that. Anybody get an answer? I got 139.6. Anybody else get that? Yes? Okay. If 6 ounces of wildflower seed can cover 10 square feet, how many ounces does she need to buy? Okay. What do you want to do? 6 ounces covers 10 square feet, and we need this many square feet covered. Can we do a little mini proportion here? How many ounces does she need? I got like 84 ounces. Did anybody else times 6 divided by 10? Yeah. All right. Let's try. Okay. What is this? One type of wind turbine's blade is 27.1 meters long. What is that telling us? If we have a wind turbine, oh, that's really bad drawing, and this blade is 27.1, when it's rotating, that's the what? Radius. Okay, it's rotating at 28.5 revolutions per minute. Is that an angular speed or a linear speed? Neither. What do we have to do to it? Got to be in what? Radians. So 1 revolution is 2 pi radians. So 28.5 times 2 is 57 pi, or you can give me a decimal. Radians per minute. And that's the angular speed. How do we change it again to linear? Anybody remember? Well, I need it to be in meters per second to be linear. So what are we going to have to do? Meters per minute. It does say the nearest tenth, so I should have multiplied that out, but anybody remember? How do you go from angular to linear? Well, I need some units here. I need some, oops, sorry, I wrote that wrong. I need it to be a distance, guys, so what are we going to multiply by? This is radians per minute. We're going to multiply it by 27.1 meters so that we get meters per minute. So 57 pi times 27.1 is 4852.8, and that's meters per minute. Did they give us the label they wanted? No, right? So we can leave it in meters per minute. I'm going to get one more done. I'm going to do this one because this is on the quiz. Okay. On quiz, this question. A flywheel mounted on an engine crankshaft has a radius of 6 inches. If the engine is running 2,800 RPMs, which stands for what? Revolutions per minute. What is the linear velocity in feet per second? Oh, this is how it is on the quiz, okay? You got to do a bunch of converting. Okay, we want linear velocity, so we need angular velocity times radius. How do you get angular velocity? You make it radians. So 2,800 pi revolutions per minute times 1 revolution is 2 pi radians. And we're done. That's an angular velocity. But what are we supposed to be finding here? Linear, so we have to multiply by the radius, which is 6 inches. But then we have to do a bunch of converting because they want feet per second. 12 inches is 1 foot. And 1 minute is 60 seconds. So 2,800 times 2 pi times 6 divided by 12 times 60, all in the denominator. I got 146.6 feet per second. Yeah. Okay, guys, this is what you need to be working on.